Hi, everyone. Welcome to the last event of day 2 of the S.Q.U.I.D Research Conference. For this event, we are pleased to introduce Nate Stemen, who will give us a talk about the Unitary Fund, their microgrant program, open source ecosystem, and the Mitiq software. Nate received his bachelor's degree from New York University in math and physics. He then worked at Overleaf as a software developer before completing a master's degree at the University of Waterloo, where he studied error mitigation and quantum circuit compilation with Professor Joel Wallman. He is now a member of the technical staff at the Unitary Fund, where he works on Mitiq, a Python toolkit for implementing error mitigation and techniques on quantum computers. There'll be some time for questions at the end, or please feel free to paste your questions in the chat throughout the talk, or if you're watching on our live stream on YouTube, we'll also be monitoring the chat there if you have any questions. So without further ado, I'd like to give the floor to Nate.
Great, thank you, Ben. I didn't know I was going to get such a nice introduction. That's nice. You did your research.
You can thank Will. Will did a lot of research as well for that.
Well, yeah. Thank you, Ben, and thank you to all the other organizers for putting on this pretty unique event. I think it's a really cool opportunity for a lot of people. So props to you guys for doing that. Yeah, as Ben said, I'm Nate. I work at the Unitary Fund as a member of technical staff, which mostly just means I write code and work on technical things, among other things. So yeah, here's my information, my email. If anyone has any questions after this, feel free to reach out to me. I'm happy to have a chat after. That's fine too. Just to give an overview of what I'm going to talk about, I'll start with some technical stuff. I'll do a little bit of intro to error mitigation, why it's important, why I spend most of my time writing code to implement error mitigation, and then I'll talk about what Unitary Fund does, and hopefully that is also of interest to some of the people here who care a lot about quantum technologies, because we do too. And I'll do my best to get us out on time. I don't want to keep people too late on a Saturday on a nice weekend. All right, so to start with the question, first of all, what is error mitigation? So in quantum computing, we often work in this circuit-based model, and so you create some circuit that you're going to want to know something about, whether it's the output state or the statistics or whatever it may be, and you want to go run that on a quantum computer, and you do that. And what happens isn't quite your circuit that you send to the computer, right? So something else happens. And so error mitigation is about accepting that scenario, first of all, accepting that we're going to have noise in our systems, and trying to make it a little smaller in whatever way that we can do that. And so you may ask me, like, okay, but we've had this idea of error correction for, at this point, nearly 20 years. Why are we caring about error mitigation? Once we're able to scale qubit architectures to thousands of qubits, then, aren't we going to be able to get rid of everything? And the answer is yes, but we're not really at that point in our quantum computing history, right? So the idea with error correction is we encode logical qubits into many physical qubits. Then you do some intermediate measurements, and you produce your syndromes, and then you're able to correct your errors based on kind of what you saw in your syndrome measurements. And that's all well, and that theoretically it works. And on the other hand, we have error mitigation, and error mitigation takes a slightly different approach. Instead of trying to get rid of errors as they arise and make sure that your computation at the end is perfectly noiseless, rather, like I said, you accept that your computation is going to be noisy, and you do other things to try and find ways to correct for the noise that has entered your system. So one of the ways you can do this is you can perform multiple different computations. I guess really the simplest error mitigation technique is to just take huge number of shots, right? Just as long as you're averaging everything out, then hopefully you can get rid of some things. It's not necessarily the best, but if you perform different enough experiments, you can find clever ways to combine results from each one of those experiments to calculate whatever it is that you're interested in, whether it's an expectation value, or some probability that actually doesn't have noise impacting it, or it impacts it less than it would otherwise. And so error correction is a great technology, and I think many of us in the quantum computing field expect this to be a very important key part of our quantum computing infrastructure moving forward. But like I said, we're really not at the point where we have enough qubits to be able to do error correction at the scale that it's really meaningful. We're working our way to having one logical qubit, and that's like a very big milestone that people are reaching for at the moment, and it's an important one. But in the meantime, we still would like to be able to use our NISQ era, our noisy intermediate scale quantum devices for something meaningful. And with the amount of noise that we see on most modern systems, it's just not possible. So error correction is scalable once we kind of get there, but it's currently unfeasible. And I'm not selling error mitigation as the end all be all, right? It's not. And error mitigation is for the most part, it's unscalable, but it's currently feasible. So a lot of the techniques that, the two techniques I'll be talking about today, and many of the other ones that are out there in the research, they don't scale well with the number of qubits or the depth of your circuit or whatever. But for some of the smaller problems that we want to run today and get more meaningful results out of, it's a good candidate to getting more meaningful results. So that's the context in which error mitigation kind of lives. There's lots of different error mitigation techniques out there. And I'll talk about this one, zero noise extrapolation, as well as probabilistic error cancellation. But just to show you that there are some other ones out here, like over here on the right, the learning-based models. If you have some circuit that you'd like to run and you're able to make slight modifications to it so that it becomes classically simulable in an efficient manner, then you can run lots of classical simulations, learn something about the noise model, and then when you go to run your classically intractable simulation, you can use the things you've learned about your noise model from the things you've classically simulated to correct some of the errors that might have arisen. Down here on the bottom, we have dynamical decoupling, which is basically the idea is idle qubits like to fall apart. And when you try to do nothing to your qubit, it's more likely to have an error than if you're doing something with it. So what you can do is you can insert these sequences, as you can see, for example, XY, XY. These are the Pauli operators, and that's, if you compile that down, that's an identity operation. But, otherwise it was just going to be identity, 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 identity. And like I said, we're not very good at doing identities on a real computer. So it's, it's almost better to be doing something than nothing. And lastly, we have the symmetry-based techniques, which is the idea that, maybe you can isolate some part of your computer that is actually doing some kind of like noiseless computation, and you try to keep your state within that kind of area of doing noiseless computation. So in between gates or in between layers, there's different approaches for how you actually implement this, but you keep pushing your state back into the noiseless region of kind of the Hilbert space, and you try to keep the state vector from going out of there. I won't be talking about those, so I'm really going to talk about zero noise extrapolation and probabilistic error cancellation, as those are kind of like the two most popular error mitigation methods that we've seen over the past few years, and they seem to work quite well. So we'll dive into those. So the key idea with zero noise extrapolation is, instead of trying to get rid of the error, pushing it to zero, why don't we just embrace that we have lots of error and make our computations worse at every step? And so if we can scale the noise up in some way, then maybe we can extrapolate back to a zero noise value. And so, here is our classical equation of motion. We have this thing. This is the classic equation of motion. But what we can do is basically add in this term here, which is our noise term. And we have this this lambda factor, which says like how much noise. And obviously this is not something that's necessarily physical, but it is a parameter that allows us to kind of manipulate some of the dynamics. So the idea here is, let me zoom in here a little bit. So let's say this is lambda equals 1, and that's kind of what happens when you run your computation on hardware, right? That's like your standard. You run your circuit, you get some noisy value, you get some measured expectation value. Let's say it's somewhere around here, and that's what you get. And let's imagine you can then run your computation again, but with double the amount of noise somehow. We don't know how we're going to do that yet, but let's say we can run lambda equals 2, and maybe we get some value that's something like this, and then you do that again for 3 times the original noise, and you get something like this. And then what you can do, just your typical extrapolation. You'd say, okay, if that's what it looks like as my noise is increasing, well, why don't I take a look at what happens over here, which is, the lambda equals 0 region, which, if we look back up here, if lambda equals 0, then we have our ideal dynamics that we're really looking for, right? That's what we want to do when we have a circuit. And yeah, obviously this is going to have some amount of error, so you never know exactly what you're going to get, but that's the key idea with zero noise extrapolation. It's a pretty simple one. I like it. It works well, and it's relatively easy to use as a user, which I'll show a little bit of how to do that if you're running on a real quantum computer. So now the question is, but how do you actually go about scaling the noise up, right? We made a nice graph, but it's not necessarily something that's easy to do. So in the paper where this was originally introduced, they were really thinking about this at the pulse level. Since a lot of quantum computers right now, at least the people who are building them, they have access to the actual pulses that they're sending to their qubits. So if they can just do the pulse over a longer amount of time, often that means you're building up the noise in the way that you would kind of expect. It's not like perfectly like, oh, I just do the pulse over twice the length and then there's twice the noise. It's not necessarily that simple, but that idea of just do the pulse slower and you can accrue more noise does hold true to some degree. And so just a silly diagram, if you have some circuit here, when you do the pulses slower, just represent that as fatter circuits, as fatter gates. That said, most of us don't have access to the pulse level control of these quantum devices. So it's important for us to ask, like, how can we still do zero noise extrapolation if we don't have that pulse level control? Is there a way for us to scale up noise even without asking them to slow down pulses? And the answer is yeah, there are a few ways, and these are often referred to as digital methods. So if you ever hear digital zero noise extrapolation or digital dynamical decoupling is the technique I talked about earlier with inserting things into idle windows. And so there's a few ideas here, right? So here's your original circuit on the left. And this top method here is called local folding. So basically what we're going to do here, let's say this first gate is yellow. What's going to happen here is you're going to do yellow followed by its inverse, followed by itself again. Obviously, this part compiles to the identity. So you're not actually inserting any logical difference into your circuit. And again, like this is going to compile to the identity. So is this. But you're going to ask the computer to do it because you're basically, you want it to do more computation in a sense than it would otherwise, so that it can have more time to mess up and make an error and introduce more noise into your system. Alternatively, instead of folding each individual gate as you go, you can fold the entire circuit. So instead of having all of these identities, right, you just have this big identity being added in front of your circuit or behind it, however you want to think about it. And this is called global folding. So first one, local folding, second one, global folding. And then the last one here is a little bit hard to see exactly what's happening, but the idea is basically in these windows, instead of inserting, instead of inserting like operations, you're just going to tell the computer to idle. So basically inserting identities. And like I said before, qubits that are sitting idle often fall apart. And so this is another good way to just lengthen the duration of your computation, and you're still able to add noise to your system, even if you're not actually doing any more operations. So those are the three main methods to scale up noise that we use, at least in Mitiq. And those are ones that are all accessible to people who have gate level access to quantum computers, which is really good because that's the thing that most of us have access to. So like I said, I'll give a demo of what zero noise extrapolation looks like, but let me just introduce probabilistic error cancellation first, and then we can jump into that. So the idea here with probabilistic error cancellation is we're going to understand that everything that we want to do on a quantum computer has some noise built into it. And so what you can do is you can use those noisy operations to try and build up noiseless ones by selective cancellation and sampling. And so one thing you can think about this as follows. Let's say you have some unitary U that you want to perform on your computer, but all the things that you can do on your quantum computer are these O sub i's. And so you can ask, like, is there a mathematical way where I can create a linear combination of these O sub i's to sum up to U? And if the answer is yes, which hopefully you should, because you should have a universal set of operations available on your hardware, then you can take your circuit and decompose each one of those operations that you'd like to perform into a linear combination. And so what you can think about here is, this gate gets decomposed into this operation, this gate gets decomposed into that representation, I should say, rather. Each gate gets a representation. And then you have like a collection of circuits. And what you can do is you can say, you want to sample from these circuits in a way where when you average them all out, they kind of, the errors cancel each other out. And so maybe on the first circuit that you perform, let me just draw this out. You're going to do yellow, yellow, followed by a blue. And maybe you do 4 more, and then maybe you do like red, third one red with the yellow one middle. And then maybe you do blue, 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 whatever it may be. But anyway, you do a bunch of these circuits, and you collect all the statistics, the results from each one of those circuits, and you're able to create an estimator for the expectation value that you're trying to measure using the following equation, where each one of these A sub i's are the things that you measure during each one of your experiments. And you have to add in some of these other factors that I don't want to dive too deep into, but happy to answer questions if people ask about that. But yeah, you can create this estimator, which is really nice because it theoretically is a zero bias estimator. So as long as you take your statistics large enough, you're going to get an estimator which converges on the ideal expectation value. That wasn't the case with zero noise extrapolation. You definitely are going to accrue some bias. And the downside of probabilistic error cancellation from having a zero bias is you do generally have a larger variance. There are some, there actually have been some recent work done to decrease the variance of the probabilistic error cancellation estimator, especially when in the case where, let's say you have 20 qubits and you only care about the expectation, or you're measuring an observable that is only non-identity on maybe like 3 qubits. So like X tensor identity, identity, X tensor, that kind of thing. We call those a local observable. And the more local your observable is, the more that you can decrease the variance of this estimator using other techniques that I'm not introducing here, but they are very, very promising in making this technique even more viable. This technique does require a good amount of work to use in practice, because you do need to know exactly what are your implementable operations, these O sub i's, and it's not always easy to know exactly what your computer can do, because just because you're asking it to do an H-gate, a Hadamard, doesn't mean it's actually doing purely a Hadamard, right? It might be doing a Hadamard with, 1% of the time, it also does a bit flip. And so you really need to drill down on what are your implementable operations, and that's not always easy to know. All right, I think that's most of what I wanted to say about probabilistic error cancellation. Before I jump into Mitiq, let's just talk about what it looks like to actually run a quantum program in practice. So as a user, what you're going to do is you're going to, take your quantum algorithm, you're going to write down the circuit for that you want to run. You'll define that in whatever programming language you want to do, whatever front end you want to use, and then you're going to send it off to the hardware or to the simulator to perform its execution. It's going to run, and then it's going to give you the results back. And when we think about how do we create some sort of error mitigation library that allows you to basically still have this same workflow, the thing that we came up with, at least in our design for Mitiq, is to do something like this. So we're going to have this error mitigation layer sit between you, the user, and your hardware. And how this works is basically you're going to do the same thing. You're going to send us your quantum program. And when I send us, I just mean, send it through one of our functions. You don't have to send us API requests or anything complicated. What you're going to do is you're going to send us your quantum program. We ask that you do one thing for using Mitiq, which is you have to define some sort of execute function, and which says like, run on IBM backend or run on such and such simulator and return this expectation value. That's the thing we ask you to put inside a function and tell us that as well. That way we can just treat it as a black box. We don't need to go and do any of that stuff ourselves. But what we're going to do is we're going to take the circuit that you want to run. We're going to generate these, for example, in zero noise extrapolation, we'll generate the noise scaled circuits. In probabilistic error cancellation, we'll sample the circuits. You'll have to tell us some other information so that we can sample the circuits effectively. But we generate these intermediate circuits. We then use the execute function that you've told us about to go run those on our backend, or your backend, I should say. And we collect the noisy results, and then we do some sort of interpolation or extrapolation, or using the estimator that we saw on the PEC slide. We combine the noisy results that we've measured, and we give you back the hopefully less noisy result than you would have received otherwise. And yeah, so this is like what Mitiq does, and where it lives, and kind of how you interact with it. We do generally try to be like a seamless interaction. We don't want you to do lots of extra work to have to use error mitigation. And with that, let me share my computer so I can give you a little demo. All right, so we're just going to walk through what it looks like to actually run zero noise extrapolation and probabilistic error cancellation of very simple examples using Mitiq. So we're just going to do our imports first. We're going to do everything working in circ. Just that's one of the easier ones. And so what's the circuit of interest that we're going to run? So we're going to generate a randomized benchmarking circuit. And randomized benchmarking circuits have the nice property that they don't actually do anything. They compile to the identity. So we know what we know what we should be measuring, regardless of how big or how deep, how wide the actual circuit is. So we can see we're just going to use one of our utility functions here, generate RB circuits. And yeah, it's really big, does lots of stuff, but it's just, you can see it's like relatively structured, but somewhat random at the same time. That's what it looks like. And then here's the execute function that we're going to use. So you can see it's just going to run on a simulator. It takes in the circuit, and then it basically is going to take that circuit, add some depolarizing noise to it, and then we're going to do a density matrix simulation. And then we're just, as our observable, we're just going to say what's the probability that it's in the ground state. So we're just looking at the 0th element of the density matrix and just asking for the real part. All right, so that's the execute function. And so now we want to run three different calculations, right? So we're going to execute the circuit with zero noise. And so that's going to be our ideal quantum computer. What would happen if we had an ideal quantum computer? We're just going to run execute on the circuit, and that's going to be, the noisy value, what happens when we run this with noise. And then lastly, we'll do z_e.execute with z_e, and we're going to give it both the circuit and the function to execute the circuit. And that's going to be, using the noisy quantum computer and Mitiq to do error mitigation. And so when we run this, it takes a little bit longer because we not only are simulating these two circuits, but z_e is going to have to run a few different circuits in order to generate the zero noise limit. It's going to have to do that extrapolation like we saw. And you can see, so the error without Mitiq is 0.35, and then the error with Mitiq is going to be 0.04. So we get quite an improvement. And as you see, it's not too much work. It's just got to make an extra call or add Mitiq as a dependency to use this. Like I said, it does require running a few extra circuits, but otherwise it's a relatively straightforward method. There's lots of parameters that you can tune in doing this. Okay, I thought I'd have autocomplete come up, but maybe not. Basically, you can tell it, how many noise scaled circuits, how exactly do you want it to scale the noise, all this sort of thing. You can try and tune those to make it work even better. But we've done also a good amount of tuning to make it work pretty well out of the box. The next circuit that we're going to use is even more complicated. It's a single Hadamard gate, and the reason I'm showing such a simple example is because doing the next part can be quite slow if we choose a much more complicated circuit. So I should say, now we're moving on to the probabilistic error cancellation section. That was z_e. PEC, like I said, it's going to require us to know exactly what our quantum computer can do. And that's not always easy because, yeah, you need to understand it exactly. When I try to tell it to do something, what is it doing? And so we have a function in Mitiq called represent operation with local depolarizing noise. And so we get a nice description of what is actually happening down here. So when I use depolarizing noise. When we assume a depolarizing noise model, our computer is not going to be just doing a Hadamard gate. It's going to be doing basically a Hadamard gate, and then you see there's a coefficient here, which is a Hadamard plus an X operation, another coefficient with a Hadamard a Y operation, and then 0.003 with a Hadamard and a Z operation. So building up these operations is not always easy, but that's the idea here, right? So we have like a linear combination of other operations that are actually going to make the Hadamard gate. And so then we can ask to execute with PEC. So we're going to pass our circ, which is the Hadamard gate. We're going to tell it the execute function, which has the noise built into it. The representations are the ones that I had Mitiq build for me. If you have a more complicated machine, you probably don't want to just use the built-in things that we have. These are just kind of just for testing, but it is kind of a good starting point. And then the number of samples for how many circuits to run and how many to sample from and generate your expectation value. And you can see when we run this, we get a 0.469. And so since it's Hadamard, it really should be 0.5, but there we go. That's how you use probabilistic error cancellation using Mitiq, or at least the simplest possible way to use probabilistic error cancellation in Mitiq. All right, and that's the demo over. Yeah,
Can I ask something quickly?
Yeah.
How many shots are executing per sample?
Let's see. Well, so this is just doing a density matrix simulation. So there's no shots parameter. It's
Oh, that makes sense. I forgot what the executor was doing.
Yeah, but yeah, that's another thing that, I mean, a lot of times you would have some sort of like shots, especially, yeah, and then you could have that be tuned as well. Thanks for the question. So that's the demo. Let me share the presentation again. All right, so that's okay, right. There's one other thing. We talked about these error mitigation methods. Do they actually work? And the answer is generally yes. They're not, like I said, they're not an end all be all to solving noise on a quantum computer. There are cases when they don't work very well, and that's that's an area of study, is to figure out when they don't work and when they do work really well. But the answer is generally, yeah, they're working pretty well. We've benchmarked quite a few of them, quite a few of these techniques on real hardware, more than just like what authors who introduce them do. That's kind of one of our things that we like to do at Mitiq, at Unitary Fund, is take ideas that people put out into the world and try to give them a really robust test across platforms, across benchmark problems, that kind of thing. All right, and so now I'm going to switch over to talking a little bit about Unitary Fund and the group and organization that has supported the building of Mitiq, among other things. So yeah, Unitary Fund is a nonprofit dedicated to growing the quantum open source ecosystem, and we're a very small team. This is everyone that works at Unitary Fund. Yeah, basically our mission is to grow quantum open source, and we do that by a few different ways. The biggest of which is we run a microgrant program. So the microgrant is a $4,000 grant to develop cool things that are happening in quantum, as long as they're kind of benefiting more than just yourself. It has to be kind of like, the one stipulation that we ask is that it's in the open. So usually for code, that means it's open source, but there's other things that we funded as well. And yeah, it's a no strings attached. We don't get any ownership of any of the projects. We just are there to provide mentorship, provide some amount of funds to get things off the ground. And so far we've awarded over 70 grants to people in over 20 countries. It's led to quite a few publications, like a bunch of libraries, and actually two startups and two nonprofits have been spun out of microgrants. I mean, I think they've been working on stuff, and then the microgrant kind of just gave them a little boost. But yeah, so it's been having a pretty good impact. Mitiq is one of the big ways that we also try and help with the quantum open source ecosystem. We think that error mitigation is kind of a core technology that is important to at least the near term quantum ecosystem. So we're here trying to develop new error mitigation techniques. We do some of our own in-house research for error mitigation, as well as just implementing some of the other popular techniques. We're in the middle of implementing subspace expansion as a new technique. And we have someone working on classical shadows. Those are two error mitigating techniques, which are kind of a little bit newer, a little bit less tested, I guess I would say. And so we're really interested in seeing how well they perform. The other thing that we do at Unitary Fund is we have a community-driven benchmarking platform called Metric, with a Q, of course. Have to have a Q in any quantum project that is in existence. So it's smushed in there. And yeah, so basically this is a platform to understand, to collect, to collate information about quantum benchmarks. The idea being that, you know, as we are building as an entire ecosystem and as a community, as we're building quantum computers, some of them are going to be better at certain things than others. And it's important to understand which computers are good at which different types of things, and, you know, who has achieved the highest quantum volume and these kind of things. And so there's this metric is, the idea with metric is to be like a single source of information for whatever quantum benchmark you can kind of come up with. So I encourage you to go take a look. It's metric.info. It's free to sign up. It's just it's a way for us, as well as the community, to kind of collect information about what's the cutting edge of whatever it may be. Like I said, quantum volume, but maybe T1 and T2 times. Anything that's important to track in growing quantum computers is most likely on there. And then we do a lot of community development. So the thing I guess I'd like to highlight and give a little bit of an advertisement for is Unitary Hack. Unitary Hack is an open source hackathon. We have this year we have 33 participating projects, and basically how it works, it's a little bit different from your typical, you know, get everyone in a room, 24-hour hackathon, try to build something. Unitary Hack is about really helping to grow what's already out there. So we have 33 participating projects, and we've distributed funds to each one of those projects to put bounties on some of their issues on GitHub. And so this year we have over 150 bounties up for grabs, with like worth over a total of $15,000. And it really ranges from, you know, whether you have skills in Python. There's lots of Python projects that are participating and are looking for help. There's some JavaScript stuff. There's an open source textbook that's participating if you're interested in quantum error correction. And it's not just things that we funded. We have a few micrograntees participating, but it's really any open source quantum project. So yeah, again, I would encourage you to go check it out. We've had, I want to say, like 20 bounties closed so far of these 150, and there's definitely quite a bit of activity on stuff, but it's definitely not too late to go find stuff and try to start hacking. So go check it out. It's at unitaryhack.dev. And then other community organizing, community development stuff that we do is mostly through our Discord. So we have community calls for some of our projects like Mitiq and Metric, but we also host community calls for some other projects as well. The QIR Alliance, which is a group of people who are meeting and organizing and thinking a lot about what does an intermediate representation look like for quantum. And if you're not familiar, an intermediate representation is basically a way to represent circuits in that can be highly optimized. So in classical compilers, we have very good intermediate representations that compilers can highly optimize and squeeze every single like drop of efficiency out of computation, and we're really looking for how do we do that in quantum as well. So if you're interested in classical computing mixed with quantum computing, I'd say these are really interesting calls because it draws from a lot of classical compilers while adding in lots of new quantum stuff. That's very cool. Q-tip is a project. It's Quantum Toolbox in Python, and so they meet every so often on our Discord just to discuss development and see how stuff is going. I think last year we had there were some Google Summer of Codes students who worked on Q-tip, and they presented on Discord. So it's that was really cool to see. And then there's the Open QAOA project, which is I think a project from Entropical Labs, and yeah, they've been meeting on our Discord as well. And the QAOA, if you're not familiar, is an optimization algorithm that is becoming increasingly popular. And yeah, I actually don't know as much about that one, so I can't speak too much about what goes on in those meetings. But yeah, if you're interested in kind of getting more involved in any of these projects, or you're just interested in seeing what's out there, I'd say come check out the Discord. We're happy to introduce you to any of the project maintainers for projects that we funded or for projects that we know about. If you're interested in contributing, whether it's through the hackathon or otherwise, yeah, we're really just trying to create like an inclusive environment where people can kind of break into the field and ask questions, whatever they may be. What we understand with quantum, it's kind of a unique position in that there's lots of people who are interested in it, but there's not a lot of people who have the particular skill set that a lot of jobs are really looking for. I'm sure many of you have seen the statistics. There's way more jobs available in this field than there are qualified applicants. So we're interested in trying to help upskill people and get people the tools they need to land a job in quantum. So yeah, happy to help people kind of break into the field. So just to give a quick summary of what we talked about. So quantum error mitigation is really a pretty growing field of research, and really its goal is to just take existing quantum computers and make them work a little bit better. I often tell people I just for my day job I make bad computers work better, and I think that's kind of the goal with quantum error mitigation, at least as it currently stands, right? As we saw, Z&E and PEC are two kind of techniques that Mitiq supports out of the box, and they work pretty well. And I definitely recommend checking them out if you ever need to run programs on an actual quantum device. And then yeah, so Unitary Fund is growing the quantum open source ecosystem, however that may be. And I'd really encourage, if people here have ideas that they think might be good for a microgrant, definitely apply. The application is pretty simple. We meet once a month to discuss the applicants, and yeah, so it's not a long waiting time. Like I said, the application is short, and they really range anything from whole new projects. Whether you have like a whole new library you want to write, but maybe also you have a library that you're using and you want to add a feature to it. That's a great application. That's a great use of the application. We're here to really the microgrant. Part of the idea behind the microgrant is that there's a few different players in the quantum ecosystem at the moment. There's researchers who are pumping out new ideas, and that's a very important part of where we're going. There's the big industry players, which are very good at taking ideas and turning them into products, and building some of the infrastructure around that. But there's still a lot of tools and a lot of like utilities that need to be built in between those kind of areas that are not necessarily incentivized in our current system to build. So a lot of researchers, they write some code for a paper and then it kind of goes by the wayside. And but maybe that code is actually really useful to other people if it was maintained and put in some sort of package. And so we are kind of there to help provide at least a little bit of resources to help make that happen. And instead of and to really grow like a rich ecosystem, we often talk about ecosystem in the sense of like, an actual jungle where, you may go to a jungle to see like the big trees that are growing out of the ground. And those are the beautiful things that you look at. But the only reason those trees are there is because they have a healthy and fertile soil upon which they can grow out of. And that's kind of the idea that we have with Unitary Fund, is to help create this rich and fertile soil that everything can grow out of, and things can be interconnected and like a jungle rather than just, some big silos standing by themselves, some big trees. And yeah, so that's really the idea with Unitary Fund. That's pretty much everything I had today for this talk. Like I said, thanks again for the organizers for hosting a really cool event, and happy to take any questions about error mitigation, about Unitary Fund, whatever it may be.
Yeah, I don't see any questions in the chat currently on Zoom or YouTube. So just feel free to unmute yourself and ask any questions you would like. So in the meantime, I have a question. What is required to apply for one of these microgrants? What do you have to put together? And what's the review process like?
Yeah, so what do we ask? We ask for a proposal. What do you want to work on? It's relatively short, just like a paragraph or two. What are the high level objectives? We ask for how you plan to use the funds. So is it just paying for your time? Do you need access to actual hardware to run some sort of problems, to do some testing? Some of the applications we received are about like putting on some sort of events. If you're going to use some of the funding for that, that's potential opportunity.
Case in point.
So funds, main proposal, and then we ask you to put together just like a brief, could be anywhere from like a minute to 5-minute video about just where you introduce yourself, you say a few words about your project, if anything has kind of gotten started, just kind of, again, like a quick overview of what you're thinking about. As part of the proposal, we do ask that you provide some information about like what already exists in the realm of your idea, so that, at least we see that, like, if you're going to propose something, what's already out there, and you're not just going to rewrite some code that someone's already written and just duplicate that. But like I said, yeah, it's relatively short. It shouldn't take too long. If anything, maybe just the video takes the longest time just to get that right. But yeah, that's it. And then, okay, so the review process, it's a panel of us, not just from Unitary Fund, also from some other organizations. We have some people from IBM, some people from Xanadu, where we kind of just get together and say, how do we feel about this application? And different people have different areas of expertise, so they're able to say like, yeah, I think this project is actually really promising in this field. Or sometimes when we don't accept applicants, we try to give as productive as feedback as possible. So we say, this seems like a good idea, but maybe if you want to apply again, more focused with this, we think we'd maybe like that a little bit more. So we do try to, provide help where we can. We're not just going to ghost you on your application. So yeah, we do try to be helpful.
And just to clarify, so you guys take application like anytime during the year?
Yeah, so maybe I can just provide a link. If you go to unitary.fund, unitary.fund, there is an apply button over on the right-hand side, and the grant application. It says on the type form takes 7 minutes. Probably takes you a little bit longer to put together the application, but I guess I can share this quickly. Yeah, so if you just go to the website down here on the right, you can hit this button, brings you to the application. Yeah, it's going to ask you for some basic information to get in contact. And then if you're interested in seeing kind of the other stuff that we've funded, you can go to this grants page and you can see all of the grants that we've made over the past few years, which is our entire history. So just to get a sense of kind of what we've accepted, what people are getting to work on stuff. I see there's a question, what can the grant money be used for? Yeah, it is probably answered on the FAQ. Yeah, I would just refer to that. I don't know. I feel like if I say something, maybe I'll say something wrong. But if you just, yeah, it's mostly just like to help you. If it's okay to pay for your time, it can be totally used for that. Like I said, if you have, if you need to use a real quantum computer and you need to pay for time, it can be used for that. Like I said, the real restriction is just we want it to be for things that are going to help the whole community. So if it's going to be a private event, it can be a little bit harder to fund things like that, or yeah, things that are very geolocated. It's a little bit harder. So I think it's generally pretty open though, as what you can use the money for.
That's fantastic. Does anybody else have any more questions before we wrap up? All right, then. I think we're good. Yeah. Nate, I'd like to thank you so much for being here. Yeah, this was a fantastic talk. I'm definitely gonna go read that FAQ and learn more about the microgrant program.
Awesome.
Yeah, and thanks so much for your awesome presentation, for your time.
Yeah, of course. Thanks again for having me.
All right. Well, to anybody watching on YouTube or all of you here, we'll join you again at 10 a.m. Eastern tomorrow for the Quantinuum Ticket Workshop and another day of presentations. So looking forward to seeing you there.